central computer of the SRC's Rutherford Laboratory is an IBM 370-195 with a cycle time of 54 nanoseconds and a core memory of 2 million bytes. Operation of the computer is controlled from a central display console. The operators are informed by the computer of impending tape and disk requirements. There are 12 self-loading magnetic tapes operating at 200 inches a second and 1600 bits per inch. Total online disk capacity is 1040 million bytes. 8,000 jobs a week are processed by the 195, and most of the output is on 4 1100 lines a minute line printers. Post office lines are used by 10 remote workstation computers. These are situated in universities and other research laboratories and are used to submit jobs and receive output from the 195. For a problem such as magnet design, the 195 is also used interactively with storage tube displays. Magnets are used in accelerators, beam transport systems, and in target and detecting equipment. For many years, the digital computer has been used as an aid to optimize the design of magnets, and recently, programs using interactive graphics techniques have been developed. With this technique, the designer can create and modify data defining a magnet by typing simple commands. As an example, consider the familiar case of a rectangular solenoid. The designer first of all sets up a graphical working space by typing in suitable coordinate limits for his problem. Next, the dimensions and the current density of the solenoid are typed in, and the program responds by displaying the cross-section. Because the coil has rotational symmetry about the lower axis, only half of the section is displayed. Because there is no iron present, the magnetic field depends only on the geometry and the current in the solenoid. The designer can straightaway determine the field at any point he desires. He simply types in the necessary coordinates. In this case, the field along the coil axis has been requested, and after computation, the values are plotted on the screen. The field along off-axis lines is similarly computed. An important factor in the design of a superconducting solenoid is the maximum field. This occurs at the center of the inside surface. The final graph shows this clearly. To obtain a general description of the solenoid field, a mapping technique is used. After changing the scale of the picture, the designer requests the program to compute the field for a number of points distributed regularly over a rectangular region. For points inside the coil, the computation is more complex, and it therefore takes longer. As soon as the field computation is complete, the designer initiates the contouring process, which interpolates the fields and draws lines of constant field. For a more complex example, consider the design of a dipole magnet for one module of a superconducting accelerator. A crucial requirement of such a magnet is that the field in the aperture must be uniform to better than 2 parts in 10,000. Here the aperture radius is 5 centimeters, and the conductors are sector-shaped elements. The data for the 4 sectors is typed in with each arc set to 30 degrees. Only one quadrant of the magnet is displayed because of the dipole symmetry. To contain and to enhance the magnetic field, a cylindrical iron yoke is required. The designer specifies the yoke geometry and chooses to represent the cylinder by 32 triangular elements. The program automatically divides the cylindrical space into the required number of triangles. Because iron is a non-linear magnetic material, the magnetic properties have to be specified. The necessary BH data is entered and plotted. Before the magnetic field can be displayed, the magnetization of the iron has to be computed. This process involves the solution of a non-linear integral equation. At the end of each iteration, the progress towards convergence is displayed so that the designer can halt the process when the problem has converged to some desired tolerance. The designer now examines the field in the aperture by requesting the homogeneity to be graphed along the mid-plane. As can be seen, the field is only uniform to 10%, and since the requirement is 0.02%, the design must be improved. In this case, the designer chooses to vary the angular arc lengths of the conductors. He initiates the automatic optimization routines which will vary the angles to minimize the field variation over the aperture. As can be seen, the new angles are now very different from the starting values of 30 degrees each. He rechecks the field, which is now within the required tolerance of 0.02%. He now focuses his attention onto the conductors, first enlarging the picture. He searches for the maximum field by computing the field inside the conductors. The maximum value of the field determines the level of current density at which the superconductor will operate. Finally, contours of the field reveal the highest peak and where it occurs. The technique of interactive graphics has enabled the designer to define his data rapidly, to check that it is free from errors, and to see the results of the computation displayed immediately in the most convenient form. He's also been able to optimize his design and to study its complete magnetic behavior in a short time.